Okay, we're starting Unit 3. This is the first lesson of Unit 3. Unit 3 is all about max and min. We have a couple of days of applications, and then we're doing a lot of other stuff that has to do with graphs. Max and mins are maximum values of a function, minimum values of a function. There's a few different types. You can have a local max or a local min, which is just a max or a min in a defined part of the graph. And you can also have global maxes and global mins. And a global max is the max of the entire function. If you can imagine a polynomial that has n behavior where it goes off to infinity, it doesn't really have a global max because it goes on forever. But some functions will, some functions won't. And again, we can talk about from advanced functions, from MHF, we can talk about polynomial functions, rational functions, trig functions, logarithmic functions, all these exponential functions, all these different kinds of functions we can talk about and talk about their max and min. Sometimes we call them extrema, so local extrema, global extrema. That just means max and min. It doesn't mean anything different, so we're going to use those terms interchangeably a little bit. In this course, we often just call them maxes and mins. Extrema, as you would guess, is similar to the word extreme. So, again, just means max or min. Okay, so in this lesson, we're going to talk about how we can find these points, and it's all about determining some properties of the graph using the derivative and what the derivative tells us about the function, and how we can look at these properties to determine where these maxes and mins occur. Okay. Another term we use for these are critical points. But there are other kinds of critical points. So critical points can be maxes or mins, but they can be other things. Okay. But for now, we're just looking at, we're looking at a few different kinds of critical points, some of which are maxes and mins, and some of them are not going to be. So that's going to be part of the process, again, in determining what kind of a critical point it is and whether or not it's a max and a min. The first thing to know in doing this is that critical points can occur. They don't necessarily occur when this is true. Again, this is part of the process, but they can occur when the derivative of a function is equal to 0 or does not exist. And you remember in the last unit when we did a couple days on Simplify Fully, the second day, that was all about stating where the derivative was equal to 0 or where it does not exist. And this is exactly why we did that, because that is how we find these critical points, and we'll learn to determine whether or not those critical points are maxes or mins. This is going to, as I say, we're going to do a couple days on applications involving maxes and mins, and then we're going to do a lot of work with graphs. And your teacher in MHF in advanced functions might have talked about this, might have said, if you're taking calculus, when we're talking about graphs of all different kinds of functions, and we're talking about locating important points like x-intercepts and that sort of thing, and then in calculus we learn how to find even more properties of these functions. And so this is the start of doing that. And this will be the first time that we're going to be using derivatives to do things. Up to now, we've just been sort of scratching the surface on how to find derivatives, but we're going to start actually using them to do things. Okay, so there's 6 different cases for critical points that we're going to cover in this lesson and in this unit. We will add on to it a little bit near the end of the unit, but for now at least, we're going to look at 6 cases, and these are all just using the derivative. Okay. Now, generally what we do in class is we sort of challenge students to try to think of what would be happening in a graph when the derivative is equal to 0 or does not exist. This is something we've already talked about, so some of these things you might know, but whether or not you can come up with all 6, that might be a challenge, but if you can start to come up with some of the ideas and then start to sort of notice a pattern, you might actually be able to, you might surprise yourself in how many of these you can get. So I would encourage you to pause the video and think about what a graph, just visualize what could be happening to a graph when the derivative is equal to 0 or when it does not exist. And then if you can get one or two of them, that's great. Unpause the video and we'll talk about it. And then at any point, you might want to pause the video again and see if you can figure out more on your own. Okay. If you can't, that's fine. But often students can get at least a few of these without any guidance. But it's the first couple are easier, and then we build from there. Okay, so I would say pause the video and try that for a few minutes. Think it through, see what you can come up with, and then we'll resume again together. The one that is most straightforward to come up with, and again, you might come up with the sketch first. You might be thinking about at the critical value whether the derivative is equal to 0 or does not exist, or probably if you may not have sketched it yet, but you probably are thinking it visually in order to come up with the classification, and you may not know exactly what we mean by classification. But one of the easiest ones to come up with, one of the first ones that you would probably come up with, would be a turning point. So this could occur in lots of different kinds of functions, but commonly we see them in polynomials. This graph is not necessarily quadratic. It looks like it might be. If I put arrows on the ends, then it certainly looks like a quadratic, but we're just going to say that we've only sketched part of it, so whether it turns back up and does something else, or whether it's a sine graph even, or a cosine graph, we don't know. That's not the point. But it has a turning point, and in this case it has a maximum. So the classification here is turning point with a max. Okay, what is happening at the critical value? Okay, these three columns are what we are going to be using moving forward to determine what's happening, because we won't have the sketch. We're just going to be looking at it algebraically, but we can use the algebra, specifically the derivative of the function, to determine these three properties, and then use these three properties to classify what type of critical point this is, if it's any. Okay? So at the critical value, what's happening? That's this point right here. Well, we call this a horizontal tangent line. Horizontal tangent line. We're going to short form that from now on, and the derivative equals 0, right? Horizontal tangent line is where the derivative equals 0. What's happening before the critical value? Well, the function is increasing. And what does that mean about the derivative? It's positive. What's happening after the critical value? Now we're starting to get the hang of this. It's decreasing. And the derivative is negative. Okay? So if you didn't come up with that first one on your own, again, you could pause right now and see if you can come up with the next one. The next one, similar to this, you can probably get. You've probably already thought of it. Okay, but again, we're going to look through all of the properties and come up with a name for it and all of that. So the next one that's most likely to come up with is a turning point with a minimum. Oops. Okay, again, it's a horizontal tangent line, which means the derivative is equal to 0. But in this case, it's decreasing before the critical value, so the derivative is negative, and increasing after. So the derivative is positive. And so to make some sense of all of this, what this means is if we find the derivative and we determine where it's equal to 0, we can check to see if it's positive before and negative after, or negative before and positive after, and that will tell us what's happening in the original function at that point. It'll tell us that there's a turning point with a max, and we'll know the x value where that's happening. So that's what this is all about. So to move forward, again, I'll encourage you to pause the video in a moment and try to think through some of this. Think about if there are any other situations where the derivative is equal to 0. And think about if there are situations that are different from these two in terms of what's happening before and what's happening after the critical value. Okay? And that might help you now that we're kind of getting an idea of what we're looking for in terms of these three columns. That might help you start to narrow down what some of the other possibilities are. So if you want to pause and think that through for a few minutes, I think that's a great idea, and then we'll pick up together again. So you may have come up with some of the other ones, and if you don't have them in the same order as I do in this chart, that does not matter. I'm going to do them in a particular order, but there's nothing really to that. What I do want to do next is I want to talk about how there's one more case of a horizontal tangent line, and there's only one more. Okay, and again, this is where the derivative equals 0. The derivative is 0. The original function has a horizontal tangent line, right? A lot of the struggle when you're first learning about calculus is mixing up the properties. A property of the derivative tells us something about the function. And if you start to think that the property of the derivative is also a property of the function, that's not the case, right? The derivative informs us about the function, but it informs us of something else about the function. And so that's just, again, takes some time to really get that figured out and consistently making that connection for yourself in your own head. Okay, so how could you have a horizontal tangent line where it's not increasing before and decreasing after, or decreasing before and increasing after? Okay, those ones are already done. If we have that, we're in one of those two types of critical points. We're a turning point with a max or with a min. So what could be happening? Well, you could be increasing before. So the derivative is positive. And you could be increasing after. So again, the derivative is positive, right? In these two situations, we switched from increasing to decreasing, or decreasing to increasing. What if we just are increasing before and increasing after? Now, this, we're calling this one type, but there are actually two cases where this happens. So we could also be decreasing before and decreasing after. We're going to call this the same thing. You'll see why in a moment. Okay. And again, the derivative is is negative before, and the derivative is negative after. Okay, so this is the only other case. Now visually, what does that look like? I'm increasing. I have a horizontal tangent line, and then I'm still increasing. So there's your critical point. Or I'm decreasing, horizontal tangent line. That's pretty bad. Decreasing, horizontal tangent line, and decreasing again. And so you can see that that is like a cubic twist that we called it in advanced functions in MHF. Okay. So if you call it a cubic twist, that's fine. We're going to call this a horizontal twist now, and you'll see why. And they're both called the same thing. They're both called horizontal twists. It doesn't matter if it's increasing or decreasing. Obviously, visually it matters, but not in terms of the classification. Okay, so that's a critical point, but that's not a max or a min, right? That's not a local max. That's not a local min. That is a horizontal tangent line. It is a critical point, but it is not a max or a min. So this is again what I said at the beginning of the video, was that some critical points are maxes and mins and some are not. And how do we know? By looking at what's happening before and what's happening after. And we can do that. By doing that, we can classify what's happening at a critical point. So you can imagine yourself taking the derivative of something, and we're going to do some examples of this in a moment, taking the derivative of something, and you've determined where it equals 0. And then you check, is it increasing or decreasing before and after? And by doing those two things, you are going to be able to determine what the graph looks like at that point. Okay? Now, I already suggested that those are the three situations, three types of critical points where the derivative is equal to 0. So the next one is going to be where the derivative does not exist. And this one's a little bit trickier, but if you would like to pause and think about it for a few minutes, great idea. Otherwise, we'll take it up together. So I'll give you a hint. This is a vertical tangent line. And we will shorten that to VTL. Again, this is where the derivative does not exist. This is not something that we've had a lot of experience with, so it might not be something that's as easy to visualize. But let's say it's increasing before, so the derivative is positive, and decreasing after, so the derivative is negative, just like we had for the turning points. What does that look like? Well, I'm increasing and then decreasing. So this is a point, okay? And you can see how you would have a vertical tangent line. Well, I better not do a dotted line because that's going to, whoops, be impossible to erase. So I'll do it in a different color. I have a vertical tangent line at that point. Remember, the derivative calculates slope. This slope is undefined because it's a vertical line. So the derivative does not exist. Again, I'm going to stop for a minute and I'm going to ask a question and I want you to think about it. What is another case where the derivative does not exist that we've already seen and possibly talked about? There's a very common place where a derivative does not exist. You may have noticed this when we were doing the simplify fully and talking about the derivative not existing. So the derivative also does not exist when there's an asymptote, a vertical asymptote. And at a vertical asymptote, let's say for a rational function, the derivative will not exist. But the function also does not exist there. So that's different. In this case, the function exists, but the derivative does not. And that's part of how we determine that the derivative doesn't exist, but it's not an asymptote. And if it's increasing before and decreasing after, then this is what the graph looks like. And what is this called? This is called a cusp. And this one has a max. Okay, it's called a cusp. And at that max point, we have a vertical tangent line. So it's coming straight up and then doing a sharp turn down, as opposed to increasing and doing a smooth turn like a turning point would. So again, we can tell the difference between a cusp maximum and a turning point maximum, in that for a turning point maximum, the derivative is equal to 0, and for a cusp maximum, the derivative does not exist, right? So there's all these different cases that we can uniquely identify. Again, the next one I think is going to be fairly easy to for you to figure out. So if you want to try it yourself, go for it. Pause the video and go for it. And it's going to be a cusp with a minimum, right? So it is decreasing before the derivative is negative. Then it's a vertical tangent line, which means the derivative does not exist. Then it's increasing after, and the derivative is positive. And again, this is all stuff that you're now going to need to know. Like, you kind of need to, you can memorize this table, or if it just makes sense to you, you'll just kind of understand it. But the idea is that we understand these are the different possibilities, and we will memorize them, we'll know them, and then when we're doing the algebra, we'll be able to classify these points. There's one more, and it is a vertical tangent line where the derivative does not exist. And just like we did before, what is the final case? So you can think about this on your own for a few minutes if you like. What is the final case different from the ones we've already done? So I'll give you a minute. And hopefully you went through the same thinking where you realized, well, I'm increasing before and increasing after, or decreasing before and decreasing after. And just to fill out the chart, to complete the chart, I'm going to write these in. But again, I think we've probably got this idea by now. So the derivative is positive, and then vertical tangent line, and then positive. Derivative is positive, then it does not exist, then it's positive, but again, the function does exist at that point. Or the derivative is negative, then does not exist, and then is negative again. And what does this look like? Okay, so again, there's sort of two different cases, but we're classifying them in the same way. So I am increasing vertical tangent line and then increasing again. Or decreasing vertical tangent line, decreasing again. Notice the difference. If I'm decreasing vertical tangent line and then increasing, I've got that hard point, compared to decreasing vertical tangent line and then decreasing again. It's got a smooth turn. Okay, and so we call this a vertical twist. Both of these could be called cubic twists. I don't know that there are official terms to these. This is what we're going to call them. This is why we don't just call that first one a cubic twist, because this is a cubic twist, but it's kind of lying on its side. And so to be more clear, we're going to call this one a vertical twist. Okay, and there's your critical point for each of them. And we'll call the other one a horizontal twist, because it's a horizontal tangent line, and then this final one here is a vertical tangent line. So there's your 6 classifications that we're going to cover for now. And there are other things that can happen, but we're not going to talk about those. We're not going to worry about those right now. Again, this is when the derivative does not exist or the derivative is equal to 0. Just because the derivative does not exist does not mean it is a critical point, because the derivative will not exist if the function doesn't exist. And if the function doesn't exist, that could be a vertical asymptote, or that could just be outside the domain of the function, like a square root function or something like that. The derivative won't exist, but it doesn't necessarily mean it's a critical point. It means it might be a critical point. Okay? So there's lots of things that we have to keep in mind and think of when we are trying to determine and classify critical points. Okay, so we're going to do some examples. And as I said, after this, we're going to do a couple of days of applications where we're going to talk about maximizing things and minimizing things. But then the rest of this unit will be about sketching and about properties of graphs, properties of functions, that sort of thing. And in doing that, we're going to be doing a lot of talking about maxes and mins, and then we will add a little bit more detail onto it near the end. Okay? So, before we move on, this is just a notation thing. Now, your teacher may have introduced this to you, may have seen it at some point. You might have seen it in a book. You might have seen it. Doubt you would have seen it in a different class. But in functions, sometimes we use this notation. Sometimes a teacher introduces it, but you might not have. Okay, but it is important to know it. It's just it's another way of saying something that we already know how to say. Which can be a bit frustrating maybe, but if you're taking, again, any kind of math, engineering, science in university or in college, then you may come across this notation. So it will be good that you will have seen it. And it's a little bit more, it's a little bit shorter. It's a little bit easier to write. So that's probably why it's a popular way of doing these things. And it's a very common notation. It's very, well used and well defined. Okay, so it always means the same thing. So we've got these, what are these, 6 cases here, and this set notation is what we already know. So for example, a less than or equal to x less than or equal to b compared to a less than or equal to x less than b, right? So that we're looking at 2 different cases here, and this would be like -1 less than or equal to x less than or equal to 3. That would be an example of that one. How do we write this in interval notation? So again, the smaller one always comes first, just like it always has to in set notation. Okay, and we just use brackets. Now, before I explain what the brackets actually mean, I'm going to do the next example, and then it's going to be easier. So how do we write it when it's strictly less than and not less than or equal to? Well, we use a round bracket, and that's the difference. A square bracket means you include the point, so we call that inclusive, and a round bracket, whether it's one direction or the other, means exclusive. You are not including the point, and that's the difference between having the equal sign or the strictly less than sign. So how would we do this one? It would be a round bracket and then a square bracket. This would be both round brackets. If it is strictly greater than something, then and it's equal to, okay, so a is the smaller thing and it goes on forever, so we use the infinity symbol. Okay, and you're never equal to infinity, so infinity will always have a round bracket beside it. And in the other case, we are starting at negative infinity up to b and not including b. Okay, so that is how we use interval notation. You can see in some of these examples we're going to use it. And from now on tests, in worksheets, in anything, that notation might be used, and so you need to know what it means. Now, the reason why this is tricky notation is mainly that that example right there, where that could look like a Cartesian coordinate, right? An ordered pair, an x, y, point on the Cartesian plane, the xy graph. So how do we differentiate between the two? Well, just with context. Hopefully it would be clear if it was talking about an interval or if it's referring to a point. Okay, and but that is, I suppose, one of the drawbacks of this way of writing things. Okay, hopefully that makes sense. Now let's take a look at the kind of questions we're going to be doing when we're starting to get used to working with critical points. Find and classify all critical points within the given domain. Right now, we're practicing within a given domain. As I said, eventually we're going to be sketching, so the domain will be everything. And I think one of our examples, we will include all points. But in the future, you will not be given a domain. It'll just always be everything. But for now, we're just doing it within a domain, and that's just going to make it a little bit less work for us. So that's really the only reason for that, is sort of to pare it down a little bit so that the questions aren't as long. So the first thing we're going to do, and you can stop and think about how you're going to do this, but we're going to organize our solution in a certain way. So that's part of what you're going to be learning. But I'm just going to go through this first one and explain the sort of step-by-step of how you are going to do this. So the first thing we're going to do is we're going to take the derivative. Now, this is an easy one because it's polynomial. Again, from advanced functions, it's really important that we recognize what kind of a function we're looking at, and that we can name it. And obviously that's going to determine how we're taking the derivative of a function as well. But then if we're sketching it, we'll know kind of what it should sort of look like. This is a degree 3, a cubic polynomial function. So I'm going to take the derivative. Nice and easy. Okay, and done. In order to determine where the derivative is equal to 0 or does not exist, we have to fully simplify. This is the fully simplify from the last unit, where the rules are fully factored, one fraction, and the fraction fully reduced and simplified as well. Okay, so we're going to factor this. If it can be factored. There's not necessarily a rule that it always will be. This one certainly is, but factor it if possible. Okay, so we're done. 4. Now we're going to examine this and determine where the critical values are. For critical values, the derivative equals 0 or does not exist. I'm going to write this over and over and over again. I'm going to write it down pretty much every time. And I would highly recommend you do too, because from now on in this course until we get to vectors, that's all you're ever going to do. Take the derivative and set it equal to 0 or figure out where it does not exist. And so you just have to really get used to that. So we're going to write it down every single time. Now, this derivative is also polynomial. It's a degree 2 polynomial function. And again, when we talk about these properties of these functions, I need to know that because it's a polynomial, it exists everywhere. So this derivative exists for all x, and that's what we're going to write. And this upside down a means, and it's kind of an a with a long line through it, for all, that means for all, right? So for all x, the derivative exists for all x. What about, and you have to say that every time, okay? If you don't say that, it looks like you're just ignoring the fact that we can have critical values where it does not exist. What you're going to realize is a lot of the stuff that we do very often, where it does not exist, is just an asymptote, so we don't really have to worry about it. Okay, but there are a few cases that will come up where it does matter, and so we can't just ignore it. We need to state that every single time. So f prime equals 0. Where's that? Now, normally we don't actually, have to show all of this work, right? But what you can do is you can take the derivative and set it equal to 0 and solve it like a polynomial function, right? If it's not already factored, then we would have to factor it now to figure out where it's equal to 0. But we already have it factored, so that's where x equals -2 and where x equals 4. Okay? So this derivative is equal to 0 in two places. Those are the two x-intercepts of the derivative. They are not x-intercepts of the function, they're x-intercepts of the derivative. Now, when I look at the interval on which we're completing this question, one of these two values is not in the domain of the question given. Okay, so I'm just going to circle it and say not in domain. Again, I want to show that I've found that value, but then I don't have to include it in any of the rest of the work, but you still want to show it, right? Don't just ignore it. Okay, so we found where the derivative does not exist. There aren't any locations in this case, but we've done that. We found where it's equal to 0. Now what we're going to do to classify is we're going to set up a chart. This is called a derivative chart, and this is a nice way of presenting the information, and we're going to do a lot of this in every unit. For the rest of calculus, we're going to be doing this. We're going to use it for sketching. We're going to be using it in all kinds of situations. So we're going to get used to this. So here's where we are going to classify. Okay, so our chart has 3 columns. The first one is going to be the interval of x that we're talking about. The next one is going to be the derivative, and then we're going to use the property of the derivative to determine something about the function. Okay. In this case, we only have one value inside of our interval. Our interval, notice, is inclusive of -5 and 3. Okay, we've only got one value in there, but you could have more, and when we do sketching, you're definitely going to have more. So you're going to have a longer table. This first example is going to be relatively short. So I'm going to start at the smallest part, at the lower bound end of the interval, which is -5, and I'm going to include that, and I'm going to my first critical value, and then I'm going to determine what happens at the critical value. Notice I did not include -2 in that interval, and then I'm going to go above it. Then that is up to and including 3. Okay. At the critical value, the derivative is equal to 0, which means it's a horizontal tangent line. That's what we know. But what is happening at that horizontal tangent line? What does it look like? What kind of critical point is it? That's what we're going to figure out next. So I am going to, and we've done this before. We did this in MHF lots, okay, where we looked in an interval and we picked some value to represent that interval, and we test it in the function, right? So I am looking in this interval, and I'm picking some value in there, which could be -5 because I include it. Again, I know that there's nothing else happening in that interval. It's not changing from increasing to decreasing in there, because if it was, I would have found evidence of that when I set the derivative equal to 0, determine where it did not exist. So I know whatever's happening in this interval, it's going to be the same everywhere. So let's pick -3. I'm going to sub -3 in to the derivative. And -3 plus 2 is negative. -3 minus 4 is negative. 2 negatives multiplied together makes a positive. So the derivative is positive, which means it's increasing. And now I can sub something in this interval. Now I can't go above 3, because if I went far above 3, if I went up to 5 or 10, that is past this critical value, which for now we're ignoring, but it still exists. So I got to pick something in this interval that's really important. So how about 0, right? And 0 plus 2 is positive. 0 minus 4 is negative. Positive times a negative is negative, so it's decreasing. And now what I can do is I can take this information and go back to my chart and realize that I am increasing before. Then I have a horizontal tangent line that I'm decreasing after. So this is a turning point with a maximum. So I've got a horizontal tangent line, and it's a turning point max at, and now I need to know the actual location because that's part of it. It says find all critical points. So I've classified it, but I need the actual point, not just the value. So -2, and be careful. This goes back into the original function, and this is what I mean by we get confused about when we're testing in the derivative or subbing into the derivative versus when we're testing in, or subbing into the original function. Like, all of these things are different, right? So it is tricky, and you just have to get used to it. So, I'm just going to punch this into my calculator, and you can check it too, but I'm doing f at -2. I'm going to write this down. Sorry, I don't have enough space. Just to show that we're subbing it into the original function, but I wouldn't normally do this. So cubed, just if you're looking back at the lesson, you want to make sure that you know what you're subbing into to get this value. And I believe it works out to 38. You can check that for me if you like. Oops. Okay, there we go. And I'm going to summarize again. I've kind of said everything I need to say in the chart there, but therefore f at x has a turning point max at -238. When we do sketching, we're not going to state that every single time, but I think it's good to summarize when we're just learning it like this. All right, let's do some more examples. So this one, B, is not a polynomial function, right? So we know that right off the bat. We know that there's something else going on here, some different things going on here. But we're going to do the same thing. We notice that this interval was given in set notation, okay, the domain that we're going to be working in. And so the first thing we're going to do is take the derivative. So again, it is the derivative of the top times bottom minus derivative of the bottom times the top all over the bottom squared. And in this case, I am going to just expand. So I've got 8x cubed. If there was more going on here and I had to start like factoring stuff out or whatever, then you would do that. But in this case, it's better to just expand. 8x plus 8x minus 8x cubed. So look what happened there. (8x cubed minus 8x cubed) means I get 8x over x squared plus 1 all squared. Okay. And these can all take very different forms. We really have to know how to look at this and analyze it and understand all the different properties that we've already done and all the different details. We've already done work in MHF on when we do things around asymptotes and x-intercepts on determining when the function's equal to 0 is when the top is 0. That's an x-intercept. Now we're talking about the derivative here, right? We're not talking about the original function. And then when the bottom is equal to 0, the function, the derivative does not exist. That would be an asymptote, a vertical asymptote, but a vertical asymptote of the derivative. That is different from being a vertical asymptote of the original function. But again, this should be familiar kind of thinking because we did it when we did sketching rational functions and we did x-intercepts and asymptotes. So the what it means in a derivative might be different, but it's the same kind of idea, like it's the same actual work, right? So again, for critical values, that's where the derivative equals 0 or does not exist. Now in this case, again, this is kind of what I was getting ahead of myself maybe a little bit. This is what I was hinting at. This derivative exists for all x. It might look like it has a vertical asymptote, but it doesn't, right? Because when x squared plus 1 all squared equals 0, that's where the derivative would not exist, when the denominator is 0. But that's going to be where x squared plus 1 equals 0, or x squared equals negative 1. And that can't happen, right? There's no place where that's true. So in this case, the derivative exists everywhere. Often with rational functions, that won't be what happens. But in this case, it does. Where does f prime equal 0? That's where the top is 0. So that's at 0. So again, in this example, we only have one critical value. So we're going to put it into a chart and figure out what is happening at that place. So we've got from -2, our interval is from -2 to 4. So from -2 at 0, and then from 0 to 4. How I write these symbols is really important. You can't write them wrong. I'm not just doing it any old way. I'm doing it that way on purpose, so make sure you understand that. And then I'm talking about the derivative, and I'm talking about the original function. So at 0, the derivative is equal to 0. I'm going to pick a value in the first interval and sub it into the derivative. Now, again, when I start to analyze this, I notice that this bottom, not only is it never equal to 0, but it's always positive, because no matter what I do, while I'm squaring that, so that's always going to be positive, and then I'm adding 1, so that's going to be positive. But regardless, then I'm squaring the whole thing again, so it's really always going to be positive, right? There's a lot of reasons why I can determine that the denominator of the derivative is always positive. So I am only looking at the numerator. If you didn't notice that, then you would just be subbing into both, and you might not realize it, but you just don't have to sub into the denominator. But in the numerator, if I'm subbing in something between -2 and 0, I'm subbing in something that's negative. I could use -1, I could use -2, and I'm going to get a negative. And if I'm subbing in something between 0 and 4, it's going to be positive. So 8 times positive is positive. So this is decreasing, and then horizontal tangent line, and then increasing. So, whoops. So this is a turning point, minimum at 0. And this one's easy to do. When I sub it in, I get 0, right? Again, f at 0 is 0. Make sure you sub it into the function. That is not subbing into the derivative. The testing is in the derivative, and then the points are in the function. So the original function has a turning point, minimum at 0, 0. All right, we still got a couple more. This one is quite different. Notice the rational exponents, fraction exponents. Okay. So when I take the derivative, I take the 5/3 out front, subtract 1. So 5/3 minus 3/3 is 2/3. 10 times 2/3 is 20/3. Subtract 1 from 2/3, so 2/3 minus 3/3 is negative 1/3. Whoops, not 1/2, 1/3. And again, I think we've talked about this. I'm hoping we've already talked about this. There are two slightly different ways that you can do this. Okay, so you got to get comfortable with a way of doing it yourself. One way is by turning this into a fraction and then getting a common denominator. So we've seen that a little bit probably when we're working with square roots. Often we do that with square roots. But when I'm working with other fractions, sometimes I use like an example like this. I am going to do it a bit of a different way. So what I'm going to do is I'm just going to factor out, I'm just kind of forcing it. And if you know this rule, then it's maybe a little bit less work. I don't know. It's a little less writing. I'm going to factor out the smallest exponent. Okay. So, and I can also factor out some coefficient stuff here. So I can factor out 5/3. If you can't follow this, then get a common denominator. And then I'm going to factor out negative x to the negative 1/3. So this is the tricky part, is when you factor, you're dividing out. So this is x to the 2/3 divided by x to the negative 1/3. Whoops, I keep writing 2. And what do you do when you divide powers of the same base? You subtract the exponents. So this is, I'm going to erase all this, so just watch. X to the 2/3 minus negative 1/3. That's plus 1/3, so that's 3/3. So that's x. Hope you could follow that. Just x. Look at that. Okay? Because I factored out the 5/3. And then when I did the exponent work, I just got x to the 1. 20/3 divided by 5/3 is 4. And I factored out the whole x part. So that's it. It's just x minus 4. Now I'm going to rewrite this in a more sort of common, familiar way. 3, and then the cube root of x. Right? So you want to write that in the denominator as a positive exponent. You don't have to write it in radical form with a square root symbol or cube root symbol in this case, but often we do. All right, so this one's tricky. This one's less familiar. We don't do this. We don't work with these kinds of functions in MHF, so I know that this is new. We've seen it a little bit in this course, but it is something you want to get used to. So don't skip these questions. Make sure you get them. These questions have unique properties when it comes to calculus, so you are going to see them on quizzes and tests and that sort of thing. Okay, same thing. We're looking for where the derivative is equal to 0, where it does not exist. In this case, there is a place where it does not exist, so we are going to we're not going to start with that, or I can't just say the derivative exists for all x. So the order that you do this doesn't really matter. F prime at x equals 0 when x equals 4. When the numerator is equal to 0. And where does it not exist? Where the denominator is 0, which is at 0. Now, if this was square root, then there would be a lot more places, because it would be whenever the denominator is negative as well, right? The radicand of the denominator is negative. But this is cube root, so you can take cube root of a negative, that's fine. You can take cube root of a positive, that's fine. But when you take the cube root of 0, you get 0. 3 times 0 is 0, and the denominator is 0. So this definitely does not exist at 0. Now, our interval, our domain, is -2 to 6. Both of those are within that domain. So we are going to include both of those points, and our table is going to be a little bit longer. Okay, so I'm going to start at the lower bound of my domain, which is -2, and then to 0. Whoops. I forgot to put X there. Okay, and then at 0, and then from 0 to 4. So notice I'm not including either of those. And then at 4, and then from 4 to the upper bound of the interval of the question, which is 6. Now, watch what happens here. At 4, the derivative is equal to 0, but at 0, the derivative does not exist. So this is the first time that we're seeing this. Okay. Now again, I'm subbing in to the derivative, picking some value in this interval to represent it. So how about -1? Or again, you could use -2 because we are including that value. So -1 gives me negative over a negative. So the derivative is positive and the function is increasing. Then I have a vertical tangent line. Then from 0 to 4, so I'll pick 1. I've got negative over positive, so this is negative, so it's decreasing. Then I've got a horizontal tangent line. Hopefully you're really starting to get an idea, a feel for how this whole thing works. And then I pick something in the final interval, so let's say 5, and I plug it in, and I get positive over positive. So the derivative is positive, and the function is increasing. So if I am going from increasing vertical tangent line, decreasing, again, we're going to go up to our chart and figure out where that is. And it was increasing vertical tangent line, decreasing. That is a cusp. Go back and figure out where we were. So this is a cusp max at 0, 0, subbing into the original function. F at 0 is 0. And this is a horizontal tangent line. So that's going to be, and it's changing from decreasing to increasing. So it is, often we do these, didn't do one of these yet, but often we do this. This is decreasing, and then horizontal tangent, and then increasing. This is a great way to visualize that this is a turning point with a minimum. Oops. And when I sub 4 in, I get approximately -15.1. Okay, so you don't have to show that every single time. You can just do that on your calculator and write it down. So therefore, our function has a cusp max at 0, 0, and a turning point minimum at 4 and -15.1. Okay, interesting. What does that mean? What does that actually look like? Well, it's increasing. It does a cusp. It decreases, turning point, increases again. And we know the location of those two places. We could find that x-intercept. And that's what that function would look like, right? So when we start sketching, we will be sketching a few functions at least that look like that. I'm just going to go back, and I'm going to do this, do it the other way just to show it, just in case people want to see that again. So what's the other way that you would do it? You would do it like this. So I would get 5x to the 2/3 over 3 minus 20 over 3 times the cube root of x. So I want to get a common denominator. So I need to multiply this by cube root of x over cube root of x. So I get 5x to the 2/3 times x to the 1/3 over 3x to the 1/3 minus 20 over 3x to the 1/3. There's no reason why I'm writing it in one form or the other form. So now I have a common denominator. So you can, some of you are going to like this better. You're going to see more clearly that this works out to x. So I get 5x minus 20 over 3x to the 1/3 cube root of x. And then I get that when I factor 5 out of the top, right? So I get the same thing. Both ways are fine. Some people are going to be comfortable doing it the first way. Some people are going to prefer to do it the second way. It doesn't matter. Like I said, make sure you practice these because they are different and they are a new sort of experience compared to what we've done in MHF. Okay, we've got one more. It's a pretty easy one, but there's a reason why we're doing it. So let's do it quickly. Notice that it's saying for all values of x. So y prime is just 3x squared for critical values. That's where y prime equals 0 or does not exist. Y prime exists for all x. Right? It's a polynomial. Where does y prime equal 0? When x equals 0. Okay, we're going to classify. I'm not going to get very many questions this easy. So when we're doing it for all values, for all real numbers, like I said, this is what you're going to be doing, generally speaking, when you start sketching, and that'll be in just a few more lessons. We do it like this. When x is less than 0, at 0, and when x is greater than 0. And if you had more critical values, then you would have a bigger chart, but that's what the top row and the bottom row of your chart will look like. They'll always be sort of an unended interval, right? Unending on one side. All right, so when x is less than 0, I'm putting in a negative, but I'm squaring it, so it's positive. At 0, it's 0. And then when I'm putting in a positive, I'm squaring it, it's positive again. So it's increasing, horizontal tangent line, and then increasing. And so what's happening here? Increasing, horizontal tangent line, increasing. That's our cubic twist, right? Or horizontal twist. So this is a horizontal twist, which is not a max or a min at 0, 0. And we already knew that because we already should know what that function looks like, right? But that's what that's how calculus can tell us sort of something that we probably already knew. Therefore, y has a horizontal twist at 0, 0. So that's a pretty good overview of the different types. The one we didn't see was a vertical twist. It will come up. We will see it. But again, you're always just looking at that chart that we started the lesson with. We're looking at it to determine, to be able to classify. Once we get this work done that we've done in our chart here, right, that's how we can figure out what type, what's happening at that location. And that's classifying critical points. Again, we're going to do a little bit of applications with this, but then we're going to be going on and doing a lot of sketching with it, and we're going to do these same kind of charts when we sketch. So we're going to do a lot of this, but for this lesson specifically, all we have to do is classify.